Okay, I think the camera's on, so I think I'll get started in a little bit here. Thank you so much for coming. I apologize for these marathon sessions. I hope you make it through most of them. I think if you have to miss one or two, I don't think that should matter. Particularly tomorrow. Tomorrow morning, I'll make sure that they don't flow as continuously as perhaps today's will. Also, remember that this is all review and it's all found in chapters 2 and 3. So you should be able to, piece together what you'll need. The other thing to note is they should be online tonight. I was told that it just takes a few hours. Now that may not be true. There may be somebody that has to push the switch, in which case they won't be up until Tuesday. But if what I've been told is correct, then you should be able to watch. If you miss one today, you should be able to watch one tonight. And if you miss one tomorrow morning, you should be able to watch it ahead of, in bed, for example. Well, maybe that's not true, but okay. So let's get started, and people no doubt will join. I hope so, because I bought 8 pizzas for lunch, so that's a lot. That's a lot of food for the 4 of us. We're going to continue our review of signals and systems in chapter 2. Last time we had a little bit of a free-form discussion, which I hope was valuable and sort of showed you how the pieces of the puzzle could fit together to make decisions. And today what I'll do is I'll proceed at a much slower pace, where we go through the usual review and hit the highlights. I'll at least remind you of the highlights. So one place to begin in talking about signals is concerning the classification of signals. And so there's a variety of ways that you can classify signals, and that can be helpful. For example, last time we talked about the energy. If the integral of the area, if you take a signal and you square it and you integrate under that squared signal, if that's less than infinity, then that's an energy signal. If you want to be practical about it, that's probably a pulse, or a finite pulse train, or a finite signal in time. If you have an infinite signal in time, and that can be something periodic that you're familiar with, like a sine and cosine, or it can be a set of random ones and zeros. So if I have a set of pulses, if I have a pulse train, but that pulse train is random. You don't know a normal pulse train that you're used to thinking about is a 1, a 0, a 1, a 0, a 1, a 0. But if it's data, it's not going to have that order, because it's got to be information, and that information has a random content to it. So it'll be 1 1 1 0 1 1 0 0 0 1 0 1. And so that could be also an infinite energy signal, because you have an infinite number of pulses, and you'd want to look at the power of that. Okay, so if the power is less than infinity, then it's a power signal. And so we can classify signals as either energy signals or power signals on the basis of those integrals that we looked at last time. Also look at continuous time versus discrete time signals. So I could have a voltage that varies continuously as a function of time. We've called that in the past, in other words, an analog signal. An analog signal. And that's pretty much what you're kind of used to seeing. Predominantly, most of the signals in this course are going to be analog signals. Most of the signals in this course are going to be analog signals. Even when we do digital signals, we'll start with an analog signal, we'll end with an analog signal. And the pulses that we end up sending down the channel, end up sending down the transmission line or the channel, will also be an analog signal, because we'll be looking at the physical layer of the problem. And even though they mean a set of ones and zeros, we represent them with pulses of a variety of shapes. And so even though they're processed as a digital signal, when they travel down the transmission line, they're pulses and therefore they're analog, and therefore they're a continuous time signal. Okay? But discrete time signals, which only occur at given times, are also overwhelmingly interesting to us. And we won't go into a lot of the tricks of the trade for the discrete time signals, digital signal processing and so on. They're useful, and they'll also teach us a lot. For example, if we need to filter a modern signal, we have two choices. We can filter it in the analog domain using resistors and capacitors. We talked about those briefly last time. We talked about a low-pass filter. And I'll go into much more detail probably tomorrow morning, where I look at a filter example more carefully than I did the last time. But the other thing that the discrete time does for us in this course. Oh, I'm sorry. Let me back up. You can filter it with an analog using components like capacitors and resistors, or you can also filter them with a DSP, a digital signal processor. And so what you would do is you would take the signal, you'd digitize it, and you'd sample it, digitize it, quantize it. We'll talk about the processes of that probably in a couple of months when we do pulse code modulation. And then we'll be able to do the filtering in the digital code domain. The advantage of that is the complexity and the realization of the filters in the digital domain can be much, much more sophisticated and much more effective than the analog domain. For example, if you wanted to build an analog signal with one pole, that's fairly easy. With two poles, that's fairly easy. You've studied second-order systems. If you wanted to do it with 103 poles, or 27 zeros, or 100 or 270 zeros, that would be ridiculously difficult. Think of all the resistors and capacitors and op-amps that you would have to do. And by the way, if you have op-amps in it, there's a theorem that says that you'll always find at least one frequency where things are unstable. The phase shifts are such that the phase shifts and the phase delays are such that you build an oscillator instead of a filter. For that reason, in digital domain, you can in fact fairly easily build an FIR signal filter or an IIR filter with any number of poles and zeros up to several hundred, and achieve very, very good phase response and amplitude response. It's a very powerful technique. It also will enlighten us what we mean by filtering, low pass and high pass filters, for example, when we look at it in a discrete time mode. Now, one of the things to think about, one of the things I want to point out, and I'll get to this again later on when we do pulse code modulation, is don't get confused between discrete time and digital. What I have up here on the board is a discrete time signal. So it's discrete in the time domain. It's discrete in the time domain, but the vertical dimension can be any voltage I want. It can be any level that I want. It's continuous. It's continuous in the y-axis. In order to get a good digital signal, first of all, I have to make a discrete time signal by sampling it. And then what I have to do is I have to assign a bin around each one of these guys. And I have to assign, for example, in this bin, one digital code, in this bin, another digital code, in this bin, another digital code, and in this bin, another digital code. And so the voltage is, any voltage that ranges in between here and here gets assigned one digital code, which could be an 8-bit code, a 16-bit code, or whatever precision that you need to be working with. And we'll go through that in some detail in a couple of months when we look at pulse code modulation. Okay? So a few things to do with continuous time versus discrete time. Anytime you can't see what I'm writing, just shout out and I'll realign things. You can take derivatives, and the derivative at any instant in time is essentially the slope of the curve of that time, the rise over the run, the change, what's changing in that signal. What's changing in the signal is a derivative. Okay? What is the analog for that when I'm dealing with discrete time signals? Does anyone in this huge sea of faces remember what that would be in the discrete time case? If I want to take the equivalent of a derivative with a discrete time signal. Okay, let's try to intuit it out. Okay? Pardon? Well, we'll get there. Let's try to intuit it out. The derivative would be the value of that point there, the value of a point just a little bit beyond it, and you would take the slope of that, so it would be the rise over the run, of that. And then what you would do for a continuous time sense is you would let the second point slide all the way back till it was just a touch more, just an epsilon more than where you started from. But effectively, it would be the difference between this guy and this guy divided by an instantaneous differential in time. Well, if I take a look at these 2 points, that point and that point, there's no n to do the limit. There's no n to do the limit. And so what I care about in I'm looking at the change of the signal from this point on, or from this point to this point, it would be the rise, the difference between these 2 points, divided by 1, which is the unit sample, the unit distance. So we call that a difference. We call that a difference. And derivatives we can write as an operator, d by dt, or delta v, delta t, if we want to approximate it. For the difference, we can write it as the voltage at some point n plus 1, that would be this guy here, minus the voltage at this guy here, one adjacent, one back. So again, derivatives and differences, and I like the word difference because it's saying what is the difference between those 2 readings. What is the difference in voltage between those 2 readings? So if an example of a continuous time signal is a voltage, maybe a sample of a discrete time signal is a sample of that voltage. Or it could be the closing value of a stock every day. Oh, but wait a minute. Stocks don't trade on Sundays. They don't trade on Saturdays. They don't trade on bank holidays. And so it's not an evenly sampled discrete time signal. You'll have the closing value of a stock on a Monday, a Tuesday, a Wednesday, a Thursday, a Friday. Nothing over the weekend. A Monday, a Tuesday, a Wednesday, a Thursday, a Friday. Nothing over the weekend. So it's a discrete representation, but we don't care about the fact that we don't even care about the fact that there's an even time scale between those guys. And so the derivative of the voltage, whether it's rising or falling, is the change in that voltage. And for the stock price, it's what is the value on a Friday minus the value on a Thursday. That would be the first difference. The second difference might be a value on a Friday minus the value on a Wednesday. So you can have higher order derivatives, you can have higher order differences as well. So things that change, things that stay the same. What's the opposite of a derivative? An integral. Very good. And that's going to be an integral sign, and that's basically just the area under the curve. That's just the area under the curve. Thank you guys for joining us. I know there's some students coming in late. Thank you. I had to get started right at 9 o'clock because the cameras turn on. But I'm glad to see you because I've ordered 8 pizzas for lunch, and so at least now that there's slightly less than 1 pizza per person, and so that's doable, right?
I brought my lunch too, so I'm sure too.
Good. So there's derivatives, and the opposite of a derivative is an integral. An antiderivative is an integral. And that's basically looking at what's going on underneath the curve. And so, let's take a look at this curve that I've drawn here. If I want the area under this curve, it's between one point and another point, say that point and that point. It's just the area under that funny-looking shape. If I happen, and I don't have to do it because it's just an arbitrary number, it's just a number, but if I want to, I can divide by the length of that time. And then what I have is the average value. The average value. If I divide by that number, I have the average value. If I don't divide that number, I have something proportional to the average. And the way I like to think about that is if a derivative is saying what's different about the points, then the average is saying what's the same about the points. The average is saying what's the same about the points. So I sum up all the area under the curve and I get an integral. Now, what is the antiderivative or the antidifference for a discrete time? A sum. Excellent. So for this discrete time signal, what I would do is if I wanted to know the sum, I would add up the value of this point, this point, this point, this point, this point, and this point. And if I take, let's see, 1, 2, 3, 4, 5, 6 of those points, and I happen to want to divide by 6, then I get the mean or the average of those. If I add up those, but I don't have to necessarily divide by 6 if it's understood. If I don't divide by 6, I get something that's proportional to the average. So if I look at this as saying this is what's different about those points, I look at this and I say, because I'm summing, because I'm averaging, I look at what's the same about those points. Let me give you an example of those two for a discrete time case. A discrete time is really nice because it helps us with our intuition. When we go and we look at convolutions, which we'll do later this morning, or maybe this afternoon, depending on how slow I meander through these topics, we'll see that taking the convolution in the discrete time case is much easier than taking the convolution in the continuous time case. And the discrete time case will bolster our intuition of what's going on that we can then apply and learn to the continuous time case. So continuous time, discrete time, filtering continuous time with resistors and capacitors and inductors, discrete time, digitizing them, a signal, and doing it with digital signal processing. So let me give you an example. There are now 1, 2, 3, 4, 5, 6, 7, 8, 9 people in the class. And we all have different heights. I'm one of the shortest in the class, and I'm at 5'6". Who do you think's the tallest? Do we have anybody who's 6 foot?
6'1".
There you go. You probably take so if I wanted to do the sum, or if I wanted to find out what's the same about our heights, what I would do is I would add my height to your height, 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 to your height. That's the summation of that discrete time signal. That's the summation of that discrete time signal. And then what I would do is if I wanted the average, I'd divide by 1, 2, 3, 4, 5, 6, 7, 8, 9. But either way, and then I would get the average height. But remember that dividing is just an arbitrary constant. Okay? And so that's an example of doing the summation or the integral of a discrete time signal. And it would be true if we all lined ourselves up across the wall, and our waveform would be our heights as we spread out in some random order, from high to low. And so we would smooth out. We'd smooth out all the differences by taking the summation. We would smooth out all the differences by taking the summation. Now, if we wanted to do the difference, we'd line ourselves up. And if you and I were standing next to each other, we would have the first difference would be 6'1" minus 5'6", or 7 inches would be the difference at my point. It'd be a positive 7 inches. And so that would emphasize what is different about our two heights, not what is the same about our two heights. Okay? Now, which one of those is a low-pass filter and which one of those is a high-pass filter? Is finding the average height a high-pass filter or a low-pass filter?
Average is low pass.
Average would be a low-pass because it smooths out all the high-frequency noise on our signal. If you think about the frequency component that goes from 5.6 to 6.1, that's a sharp frequency component. That's a sharp rise. And that information is lost when we take the average. Does it stand to reason then that the difference would be a high-pass filter? By the same token, the high frequency, what's the same about our heights? What's the same about our heights? Which is, let me try my math real fast. That's 5'9.5" inches. The thing that's same about our heights is 5'9.5" inches. We lose that when we take the first difference, and we talk only that the difference between our heights is 7 inches. So I could be a foot, and you could be a 1'7", and we'd have the same value for that difference. I could be 100 feet, and you could be 100'7" inches, and we would get the same difference. So what's the same about our height? The fact that we all struggle into an airline seat, regardless of our height, is lost in that. So the high frequencies are lost in the differences. The low frequencies are lost. The high frequencies are lost in the sum. The low frequencies are kept in the sum. The high frequencies are accentuated or kept in the differences. The low frequencies are lost in the differences. Okay? So you've looked in networks, in circuits, you've looked a lot at derivatives, at high-pass filters and low-pass filters. Now I'm showing you what they mean in a discrete time sense and a continuous time sense. And that's really useful because now, if we're doing an algorithm, if we do a system design where our analytic mathematics says that we want a derivative, we scratch our head and we say, how the heck do we realize that? As engineers, we not just do the theory, but we have to build a board to realize, to calculate electronically at gigahertz and gigabits per second and higher what the answer is. So how do we realize that? What hardware do we arrange to realize that mathematical function? If the mathematical function is to take a derivative, then we have to build a high-pass filter. The capacitor that blocks the DC and lets the AC through the resistor. If we want to do an average or a sum, then what we want to do is a low-pass filter. Okay. There's a graph I probably should have drawn yesterday that I'll go ahead and do now, or the other day. Do you remember I digressed and we looked at this low-pass filter? We know that for high frequencies, this is a short to ground, and so the high frequencies vanish from our resistor, our load resistor. If on the other hand we have low frequencies, then the low frequencies see an open circuit to ground, and they all route directly to the resistor. So if I now draw a signal, there's my low frequency content, and on top of this content, I have noise. Then the noise, the high frequency noise, will see a short circuit and get routed to ground. The low frequency, and I sure as heck hope that's my signal, the low frequency signal, the underlying curve, is what goes across the resistor. So that's simple. That's a very simple trick of averaging out the noise. So the noise is averaged out. Yes, sir.
What is the noise exactly?
Well, okay. In my example, I had the rare luxury of identifying to you what I thought the signal was, which was the red line. And I also, in my example, had the rare opportunity to just tell you exactly what the noise was, and I happened to put that at a much higher frequency. So let's think about it this way. Well, I'll give you two examples. I'll give you an example, from say electronics. Supposing I've got a slow signal that varies over minutes. The temperature of I don't know, something that's cooling in a refrigerator or a bath. I take a hot boiling water and I put it in a refrigerator, and I stick a thermometer in there, and in a few hours it's cold. Over that time, I have a very slow temperature change. Okay, and that would be my signal. And so I know from the physics of the problem that my signal was going to vary at a slow frequency rate. On the other hand, I'm doing an electronic circuit, and so I plug it into the wall, and my circuit, everything gets corrupted by 60 hertz noise. And so the 60 hertz noise would be a sharp hash on top of that temperature. And so if I low pass filter, if I filter out the 60 hertz noise, then I lose that noise, and I keep my signal. So sometimes the physics of the situation tells you one from the other. And so you can look. Yes, sir.
Forgive me for stating this probably obvious, or if I'm wrong completely, but so the order that if you have something where you have multiple stages of filters, the order is extremely important. If you have frequency crossover, or is it?
If no new frequency is generated, if we're only dealing with linear systems, then you can show that the cascade of filters is merely the product of those filter responses. Right. And so if I eliminate one frequency early or late, it doesn't matter. It's still gone from my problem. Okay? If I first block all the people who are wearing blue shirts, and then I block all the people that are wearing red shirts, that's a sorting problem. And then in one system, and then another system, I block all the people wearing red shirts, and then all the people wearing blue shirts. I'm sorry, but the four of you are still out, regardless of whether you got rejected on the first pass or the second pass through the filter.
And is this like normalization?
Don't take it personally. It was just an example. Sorry.
No, is this like normalization when you say averaging? Like for white noise, or?
I would just say I'm just going to stick with the words that I've used. Okay. Because I'll reserve normalizing a signal from something very different. Okay. So this is just averaging. It's just low pass filtering. And again, what I want you to do is to start to get comfortable with you've all done averages. In for example, in a wonderful probability and statistics course, what is it, 3341? You've all done averages, and then in circuits, you've all done low pass filtering, and you probably haven't thought about those to be the same. And so that's the first thing I'm going to start, and I'm not going to win on this one lecture, but over the course of the semester, I'm going to try and get you comfortable with that idea. Okay. You know, another example. We talked about the financial applications of this. We talked about stock prices as a discrete time signal. An example. So consider the day traders of a stock. Yeah, you know, you probably know some. They go into the dorm room and they trade stocks like they were gambling, and they don't really care about what the stock is. You know, they don't care if it's an airplane stock or an airline stock. They don't care if it makes, you know, brooms or computers. They're just looking to look at what the momentum is, what the press is thinking about doing. The day traders are just trying to get to lock in a profit over very, very high frequency changes in the stock. Well, if you're an engineer at that company, or you have stock options in that computer company, then you don't care so much about what's happening on a day-to-day basis. What you care about is what's going to happen when your options vest. And so you're motivated to look at what, if we developed a computer and we sold 10 of those this week, how do we sell 20 of them next week? How do we sell 40 of them the week after that? So you're driven by the longer-term, slower frequency swings, what's happening on average over your vesting period. Okay. If you don't know the stock option world and the vesting world, as an electrical engineer, I encourage you to get to know it. Because it is one of the ways that we get rewarded, we get paid, and we can get, if we're lucky and we get on with the right company, we can get inordinately wealthy that way. You won't make millions in your job, as an engineer. You will make millions as your job as an engineer with options, with stock options. And so in fact, I should soften what I said. Most of the people at the companies that I worked at, they kept a ticker of the stock price on their computer monitor, always driving. So they actually did watch the performance of the stock on a minute by minute basis. But they couldn't do anything about it. They weren't day trading it. They were locking in from what they were going to do. Okay. So those are two examples of filtering problems. One from the analog world, an instrumentation example, and the other from a discrete time world, which happened to be a financial example. And I picked the financial example partly because it's useful and interesting to you, or will be, and partly because it's an example of a discrete time signal that's not sampled evenly, that comes from a completely different world. Okay. All right. So I rambled on along about that, but there's some very, very, very interesting topics behind those simple concepts that a mathematician would just have dispensed with that in a nanosecond. But our job is not only to understand, not only to be able to do the mathematics, but it's also to be able to look at the interpretation of it, because we're going to be looking at these systems, these comm systems, and we're going to see a box. And we're going to have to figure out what goes in that box from an analytical perspective, from an analysis perspective or design perspective, and then we're going to have to realize it with components, either a DSP chip, an FPGA, or if we have to save money, a simple RC circuit, a simple LRC circuit. So when we do that, we have to have a much more intuitive, a much more sophisticated understanding of what that mathematics is. So the takeaway is, when you see a derivative or a difference, you're going to do a high-pass filter. When you see a sum or a sum or an average, you're going to do a low-pass filter. Okay? All right. Now, we're still classifying signal. Well, I'm sorry. We're still under the continuous time and discrete time world. So if I have derivatives and differences, then we also know we can have differential equations. And in the discrete time world, we'd have difference equations. We would have difference equations. And so, in fact, the differential equations will describe the higher order filters. If we were doing that in say, differential equation world or physics or early in networks, we'd be looking at a second order system, the second order differential equation for an LRC circuit. The difference equations could be higher order difference equations where we do averaging and differencing from multiples, not just adjacent samples, but across samples that are separated by 2, 3, 4 and so on. And so you can see right there that the power of doing a rolling average in a difference equations, you have so much more license for what your algorithms look like when you're working with the difference equations or digital signal processing than you have with differential equations, which are analog. So that's one of the secrets. That's one of the secrets to creating better systems with digital signal processing. Is your algorithms can be so much more thoughtful for exactly the same development time. And if you make a mistake, you can reprogram these DSPs and FPGAs even in the field. Even in the field. So and that's a huge power. So because of that, that's that basic truth, that basic task of signal processing, moving from differential equations to difference equations, and all the power, looking at the meaning of a plus and a minus, looking at the weight, the relative weights behind those signals, rolling averages, rolling differences. Those breed much more careful algorithms that tease out much more information from your waveform. Okay. Now, things that we'll get to pretty quickly. If I want to represent a continuous time signal, in the frequency domain, then what I do is I do a Fourier analysis. I do a Fourier transform, or you also have been taught the Laplace transform. I won't mention the Laplace transform very much, other than to point out that there's, with great apologies to the mathematicians and the coding theory people and the control theory people, I don't see a huge amount of difference between the Fourier transform and the Laplace transform. Exactly right. So, I can even put that back if you want.
Okay.
So the kernel for the Fourier transform is either the j omega t or minus j omega t, depending on what textbooks you're using, and the kernel for the Laplace transform is either the st. And S is equal to sigma plus j omega. So you're exactly right. If I drop the sigma, I reduce down from a Laplace transform to a Fourier transform. But on the other hand, if I do omega is equal to omega prime omega double prime plus j omega prime, then the j omegas cancel out, and I see that omega prime plays the role of sigma, and omega double prime plays the role of omega. So I can go from the Fourier transform up to the Laplace transform if I want to too. Okay? So there's great utility in having the sigma in there if you're doing controls. For comm systems, maybe not so much. Regardless, you don't have to know that you're not slamming the door on one when you're picking the other. Okay? So you can have your cake and eat it too. For the discrete time world, there's the Z transform, where every delay block is represented by a z to the minus 1. So if I delay a signal, then I increment an n to an n plus 1, and then I multiply it by I can multiply it by a z to the minus 1, and this reduces a differential equation to an algebraic equation. This reduces a difference equation to an algebraic equation. Oh, and by the way, if I do things like think about what a delay is. A delay is a phase shift, and a phase shift in the Fourier domain, and we'll go over this down the line, but a phase shift in the Fourier domain is multiplying by e to the I delta. And so So from there, we point out that a Z-transform is as good as a Fourier transform, which is as good as a Laplace transform. Wow. So in fact, if you're modeling filters, in the Z-transform domain, you can realize them in any other way as well. So it is right in other courses to emphasize the differences between the Fourier transform, the Laplace transform, and the Z-transform. But I also, in this course, want to take a contrarian view and argue that there's also a lot of similarities between the Fourier transform, the Laplace transform, and the Z-transform. And that in many instances, they can be used interchangeably. And so hopefully that helps you unify the huge amounts of knowledge that you've gained over the last few years of courses here. You might, I imagine, maybe I'm wrong, but I imagine you guys showing up in this course with all these buckets of knowledge that you've accumulated in this course, and this course, and this course, and never shall those notebooks meet. Right? What you learned in probability and statistics has no bearing on signals and systems, and which has no bearing on networks. But because we're putting all those pieces together in this course, I want you to start to make cross links. And once you do that, the chore of keeping up with all these notebooks is so much easier. You will have much more confidence in your knowledge, and you'll be able to keep track of a lot more knowledge. And so that's by simplifying in this manner and by seeing cross connects, it's very liberating. It's very, very nice. And that's one of the reasons why I like to do this review the way I do this review. You've seen all this stuff before. But I'm trying to cross-link, trying to make some cross-links for you. Okay, let's shift gears a little bit. A couple of you came in late, so let me just put the slides up again. Oh, I don't know. I didn't keep track. But you were. How late were you? You were 3 pieces of paper late, or 2.5 pieces. We started at 9, and that's not my bearing. The cameras go right on at 9, and they go right off at 10:15. They'll come right on at 10:30. Okay. So what we've done, we've looked at classifications of signals, and one way to classify them is energy signals versus power signals. Another way to classify them is continuous time versus discrete time signals. We looked at derivatives and differences for discrete time signals. We looked at integrals for continuous time signals and sums for discrete time signals. We looked at what that meant from a filtering perspective. Integrals are low-pass filters, averages, and derivatives are high-pass filters or differences. Okay? Oh, sure. Sorry. It's all going to be available for you online, so you can. But I understand it's you all in your notes. Yes. Good. Second page and different differential equations versus difference equations, Fourier transforms and Z-transforms. Okay. One more point on the Fourier transforms, and I'll just pick on that for a while. You can Fourier transform many things. You can Fourier transform a signal. That's usually what we think about. You can also Fourier transform a system or a component. For example, when I write this lumped impedance, what I'm really doing is I'm Fourier transforming that element. The d by dt is going to 1 over j omega c. 1 over j omega. So I'm looking at that as I'm saying I'm Fourier transforming that circuit when I go to the lumped element. Okay, which is maybe you don't think about. And similarly, you can also Fourier transform operators. One example might be you have a delay operator, and you Fourier transform it into an e to the I delta. Okay, so we could be expansive in our interpretation of what it means to work with with all these tricks. Okay? Probably, again, tell me if I'm wrong, because I'd love this feedback, but probably you know all those facts, but you've never clicked it together in exactly that way. That's my guess. And that's the reason for the way I present this. And the reason why I'm asking you for that is if I'm wrong about that, I'm going to adjust my lectures in the future. But I think I'm making an assumption that's correct. Okay. Another classification of signals. Periodicity, and whether a signal is periodic. So, first I'll talk about what it means to delay a signal. So I have a little pulse, and in this case that pulse, I've drawn it as an even function. There's no real reason for that. It's just a little triangular blip that lives at t equals 0. And I'll just call this x of t. And if I delay it, so that it now occurs at a later time, say A. This is a delay block. So I take this signal and I route it through a delay block. If I care, I can call that unit delay, or e to the minus z, or e to the minus 1, or e to the minus a, depending on the notation of my problem. So x of t will now become x of t, and I have to worry about my minus sign. I believe a minus sign, and check me on that, a minus sign delays the element. So at t equal to a, this looks like t equal to 0, which gives me the maximum value of that pulse. So a minus sign is a delay in time in the positive direction. Okay? And I never remember that, so I go back and I think about what that means. Okay? And this, notice that the way I've described this is this A is a shift in time. It has units. It has units of seconds, or whatever time is. And we know that because, look, I have a t here. That has units of seconds. And I'm adding or subtracting from it a number, A, and that better have the same units. Otherwise, I'm subtracting apples from oranges. So A is a delay in terms of seconds. Okay? Delaying is really useful. Delaying is really useful. I'm going to suggest to you, and this is a horrible digression. I shouldn't do this, but I can't resist. You'll learn that about me. I will meander off the path of my lectures. I'll try to tell you when I'm doing that. You will sometimes want to drag me back from the 1920s into the present. Maybe. But one of the things that I'd like to point out to you is that a simple filter the only thing it does is it splits signals. It splits a signal into a sum of parts. It introduces relative delays for each of those parts. It weights them. And then it puts them back together. That's all a filter does. A filter is something that takes an input signal, it splits it up into a bunch of parts, it delays those, it weights them, puts them back together. You can put it together In the future, you can put it together in the back. Feed forward or feed back. But that's all a filter. That's really what a filter does. Sorry. If you can't see the paper, you should yell at me, even if it is a digression. Okay? So we'll get into that a little bit more, but I just wanted to get on the record for saying, for starting you to think about what filters are from a physical realization perspective. Okay. We bring you back on track. This is what we had before. The delay of the signal. Now, there are some signals are magic. And I use that word because it's so rare. I use that word because it's extremely rare. This is an extremely rare situation that x of t if I find the t, and that capital T can be plus or minus. So I can be shifting it back or I can be shifting it forward. So I'm not too worried about that plus sign. But if I find a capital T, if I find that capital T, so that all the values of x of t are equal to all the values of x of t plus capital T, then the signal repeats with a capital T, and I call that signal a periodic signal. I call that signal a periodic signal. And that it is periodic with a signal with a period T. Most signals are aperiodic. By that I mean not periodic. So don't get your hopes up. Don't get your hopes up. Most signals are non-periodic. Certainly our message signal, M of t, which is comprised of a random waveform, a waveform that looks random, even though it's rich with information. Not a prayer that it's going to be periodic. Right? If it's periodic, it's probably some test signal, like a tone modulation, like the instant where a opera singer belts out a note and holds that note, a flat A, for 30, 40 minutes on one breath of air. That's a joke. then that would be a periodic section of the signal. But it's rare. And let me just do a quick example that kind of emphasizes some of the manipulations that we like to do. So we know we would not be surprised with our large amount of engineering knowledge to date. We're not surprised when I say cosines are periodic, because they're waves. They go up and down, up and down, up and down, up and down. Very boring tone signals. Okay? So, to show that a cosine is periodic, I have to show that cosine of omega t plus capital T is equal to the cosine omega t. That's the definition. Cosine of omega t is equal to cosine of omega parentheses t plus capital T, close parentheses. Okay, so I have to show that. And if I do this, what's my biggest tool that I use for these kinds of things? Trig identities. Okay, reach for those. I last semester, I'm not going to promise what this semester will hold, but last semester I got a comment from one of my students that said, Duncan, or maybe it was Professor McFarland, I don't care. But Professor McFarland, you kept emphasizing trig identities, but you never asked us a problem with them. And that was an oversight on my part and just a random element, because usually they're gonna pop up in some way, shape, or form. I hadn't even thought of it, but I didn't go out of my way to do that or not do that. But he sensed a conspiracy, and it just happened. I promise. So trig identities: cosine A, cosine of B, minus sine of A, sine of omega capital T. I'll just make a quick observation about this trig identity. And that is, I know that my original signal was even. And this I'm pretty sure is right because I've got an even times an even, which is an even. And I've got an odd times an odd, which is an even. So this representation is obviously an even function, and that's what I need to match up with that and that. So I get really confused about cosine of A plus B versus sine of A plus B and so on. And then this minus sign I have to kind of think about separately and show a special case. Okay? Turns out that this trig identity we'll do a million times in this class, so another reason to kind of go through this a little bit more. And then we see that if capital T is equal to 2 pi over omega, and this is just hunting and fishing. This is just fishing around a little bit to find what our capital T is. If that's the case, then this trig identity changes to cosine omega T, cosine of, omega times 2 pi over omega, where those omegas cancel, minus the sine of omega T, the sine of omega, 2 pi over omega, so the omegas cancel. Did I do that right? Okay, so the cosine of 2 pi is 1, and the sine of 2 pi? 0. So whatever this minus sign is doesn't matter. Phew. So this whole term goes to 0, and this is equal to cosine omega T, which is what I had on the right-hand side. So that's my proof. Okay. Notice that if my period is a little bit off, so if I have to realize this delay, if I have to realize this phase delay of 2 pi, then I may not quite I may have a little bit of extra wire in there, or I might have a little bit of extra capacitance, part-to-part variations. In which case, if I'm realizing this, well, gee, this cosine omega of 2 pi won't be quite 2 pi. It'll be 2 pi plus some small error. And so this number will be a little bit less than 1. That number will be a little bit less than 1. If I try to realize this in a circuit, and I have to build 100 circuits, and I buy capacitors or resistors that just are a little bit off. And so I'll have a small degradation or a small impairment in the operation if I'm relying on that to be 1. And similarly here, if I rely on this to be 0 and it's not quite 0, well, all of a sudden this oscillation rears its ugly head into my problem. Uh-oh. Okay. So there's maybe not very relevant in this particular example, but there's 2 steps to an engineering analysis or design problem. One is to do the answer, and you're all very good at that. You all pat yourself on the back, put a little big box around it, and say, I'm done, I go on to the next problem. But if you're really building a real system, if you're really thinking about things, well, you have to do maybe an error analysis or a sensitivity analysis, and you have to look at imperfections in your realization. How robust is it to realization issues? How tightly do I have to spec that delay line in order to be able to meet a margin requirement in my system? Okay. Have I milked that example for as much as it can be worth? Good. I don't mind going slowly, especially when we're thinking in terms of that. I won't go through this shifting in time ahead and behind. That we know that. I would like to talk a little bit about time scaling, though. And I'll redraw my pulse just a little bit so that I have a T1 and a T2. And then because I'm bored of writing X of T, I'll write G of T. I did change the pulse, so I'll change that a little bit. And scaling means that if I have this nice pulse, I want the things to happen faster or slower. I want to dilate it or contract it. And so, for example, what if I have G of 2T? Well, that means that things happen twice as fast. Oh, gee, let's see. So that things have to happen twice as fast. And so what that means is my pulse will start off and rise quicker and fall quicker. So it will go up and it will come down, but in a time that's much faster. And one way to think about that is to think about the difference between cosine t and cosine omega t. Right? Think about cosine t and cosine omega t, or cosine omega 1t and cosine 100 omega 1t. The higher frequency means those ripples on the sine wave happen much faster. Okay? And that's all that's saying. That's all that's saying. That's just a special case. On the other hand, if I want things to go slower, I divide by that factor. And so my pulse gets dilated out. It gets longer, it gets spread out. One more manipulation with time. One that we may find useful when we do convolutions. I have some funny pulse, some energy signal that looks like this. I'll call that f of t. And then if I care about what f of minus t is, then I flip the whole thing around the axis. Okay. So you notice that this guy was sitting out over here at 12, and now it's at minus 12. 12 being an arbitrary constant. Okay? So it's flipping out somewhere over here, and it flips back with minus t. So that's a flip or a rotation around the axis. Last time we talked about even functions and odd functions, well, a little bit. And so that property, that time reversal property, is one of those. Is a very important part of that case. Okay. All right. Let me go through. I'm going to try and review as much as possible over the course of these lectures, so that when people come in late or when they're watching them online, and they can see where we've been. Usually when I lecture, I write on the blackboard, and if I do my lectures perfectly, I start at the hour, and at the hour 15 minutes, after an hour and 15 minutes, I'm on the other side. And so usually the students have the luxury of seeing the entire notes, minus the digressions and minus the interesting war stories that I tell. Interesting being my description, not yours. They see it all at once, and so with this writing, I have to modify it a little bit. So again, we're talking about signals. We're blending a little bit the classification of signals with the manipulation of signals. We talk about filtering. We talk about the role of difference equations, differential equations, particularly in light of filtering and system descriptions. And then Fourier transforms, Laplace transforms, Z transforms. We looked at classification of signals from a periodicity perspective, but that meant that we had to learn how to delay a signal. And so we learned how to, we reminded ourselves how to delay a signal. And then what if you delayed a signal and nothing happened? That was a pretty magic effect. That's a periodic signal. An example of a periodic signal is a cosine. And so a simple example to show that a cosine is a periodic signal. Scaling, something we do all the time when we look at different frequencies of a cosine, for example. And then time reversal, which gets us into signals that are even, odd, if they have parity. Okay? All right. Moving on a little bit more. We had a very loose lecture last time, where we looked at where we looked at some of our favorite functions and their functions in the frequency domain. And so I want to continue on that a little bit more rigorously. E to the minus alpha t is one of our favorite functions. We might want to write that e to the minus t over tau. Alpha is just 1 over tau. Exponents, like sines and cosines, like many other functions that we see, are transcendental, which means that if I do their Taylor series, they have an infinite polynomial that describes them, which means that whatever I take an exponent of, or a transcendental function of, had better not have any units. And that's what's being illustrated perfectly in this example. T has units of seconds, and tau will have units of 1 over seconds. Think RC time constants. R times C will have units of seconds. And if we want some verification of that, 1 over j omega c has the same units of r. Multiply through by r, I have 1 over 2 pi inverse seconds, which is seconds, so r sine c is dimensionless. RC has to have units of time. Okay? So just a little note on that it's all is well in the world. I can have sinusoids. Sine of omega t and cosine omega t. But really, I've said absolutely nothing new. Because of Euler's identity, e to the I omega t is equal to cosine of omega t plus I sine of omega t. I know that we're electrical engineers, and so we were supposed to use J for -1. But I've read a lot of different textbooks from physics and math and electrical engineering, as, by the way, you have as well. And so I depending on where my head is at and what link to my distant and dark past, and at times sordid past. Oh, I should have said that on tape. I don't know exactly what I will sometimes use I and sometimes use J. So the point of that is to say that when you see, if you're very comfortable with J, which I imagine you are, if you see me use an I, don't freak out. Just make a small notation if you care about it, or just know that I'm often a wonderfully happy math course somewhere in my past, or physics course somewhere in my past. Okay. So the point of this is that with this Euler's relationship, I don't really care whether I have a real or an imaginary, or I describe a signal as a sines or exponentials, because I can go back and forth, again, with complex frequencies or complex taus and alphas. Okay? And again, I know a lot of you are taking fields and waves this semester. And I guess I want to digress a little bit on that. When you see in fields and waves, when you look at, say, propagation through a lossless material, and then you look at it again through a lossy material, think about what you're doing. You're making this guy here, you're just changing that to make it complex or not. Okay? And again, maybe make a point, Laplace transform versus Fourier transform. And then the second thing I want to point out on that, and this is completely an aside, is when you look at EMAG, try to look for signals and systems concepts in there. Try to look for Fourier analysis. Try to look for Fourier techniques. Try to look for even convolutions in there. They'll be there. And that's one that's very interesting, because a lot of people who teach fields and waves, they may not have come out of as strong a double E background. They may be coming from a more physics background, and they won't necessarily emphasize the signals and systems part of EMAG. But it really is. Once you see that, you will be drastically bored by 20% or 30% of that course. And that's a good thing, because there's plenty of other stuff to stress you out about. Okay? All right. Just a quick secret aside, since you guys showed up early on a Saturday morning. All right. One more thing that we'll start, but we'll have to get to next time, which next time being about 15 minutes from now, is another one of our favorite functions, which is this impulse, delta of t. And there's, if we were talking about discrete time signals, so I'm also going to talk, we're also going to be able to talk about discrete time delta functions as well. And this is completely a fictitious function, even though you can buy approximations to it, and you can realize approximations to it. Sometimes pretty good approximations to it. But yeah, it's a problem that doesn't. It's a function that doesn't exist. And the reason it doesn't exist is because if I sketch this in the time domain, then this has an infinite magnitude. So this spike goes all the way through the roof, or I guess through that wall, since I'm horizontal and not vertical on my board. And it has a zero width. But somehow, magically, the area under the curve is equal to 1. It has a finite area. So it's an energy signal. So it has a finite energy. So somehow that happens, and we'll have to wait till next time to see it. This delta function here is just a single unit spike at n equal to 0. And it's much easier to deal with, because it already has a 0 width, and now it just has a 1 for an area, so it has a height of 1. So this delta function, the discrete time delta function, is much happier. And by the way, these are not the only kinds of delta functions out there. When you start working with matrices and even tensors, you'll have Kronecker delta functions and so on and so forth. So this concept of a delta function is actually much more general than we give it credit to. And with that, I'm going to quit, I think, 1 minute early, and we're going to take a 15-minute break, and we'll come back at 10:30. I brought snacks this morning, and thank you for bringing coffee. Appreciate that. And so we'll get started again at 10:30, right on the dot, because that recording sign is going to go. All right.